So, so today we are going to talk about this OWL scale and flexibility in distribution of hot content. This paper is published by Meta people in OSDI, and so I'm presenting this paper. So what's the overview of this paper? So they say that we have built a system that decentralizes data plane with centralized control plane. They have a concept of peer nodes, which they say, since it could be millions of processes, and so it has to be simple, and it's just a simple state machine mechanism implementation. Main policy decisions and everything is kept with the other type of node or processes that is known as the trackers. They are customizable, where to get the chunk from, and which peers to put that chunk to. All these things and policies and locality awareness and everything is put in the trackers. So their claim is that when we talk about centralization, first thing comes to our mind is that there can be scalability issues. So they claim that they have built this system with centralized control plane, and in fact, it's not a barrier to their scalability. The numbers that they tell or talk about is they were able to push 800 petabytes of data per day to millions of client processes. And this OWL improves over BitTorrent by a factor of 2 to 3. So let's talk about the requirements. So they say that they have a private cloud, and efficient distribution of large hot contents to end host is of their primary importance. So there are a couple of points in the requirements that the scale is needed. So same content may be read by millions of clients around the globe. Size of objects can range from 1 MB to few terabytes. Hotness is also another aspect that needs consideration, wherein clients can read the same chunk of data within few seconds, or it could be spread over hours. So their example sample applications were executables, code artifacts, AI models, search indexes. So what they say is that for distribution requirements, there are two fundamental requirements: that the content distribution must be fast, and the content distribution must also be efficient. Efficient in what aspects? They talk about efficiency in aspects of scalability, network usage, resource usage on client machines, and reliability. So trackers, as I already said, have the policy decisions. And they say that centralized control plane is not a limit to the scalability. Yeah. So continuing further. So prior solutions, what are the prior solutions that were deployed at Meta? So they say that there is, so before that, they say that there is no correct balance between decentralization and centralization that was happening in prior solutions. Also, there was not sufficient flexibility to meet all kinds of requirements from different services that Meta requires for content distribution. So one type of mechanism or system that they used was hierarchical caching. It is multi-level caching. The issue with that is it is difficult to scale, as and when they every year on year basis they saw that their workload kept on increasing. So a lot of nodes or hosts were needed to maintain this cache hierarchy. They talk about somewhere around 23K nodes, if I'm not wrong. And the other issue is because of hot content, there are load spikes that happen. And they say that the way they used to handle it was using quota systems. But then because of the in-place quota, whenever the spikes were handled, it left clients being clients not given data, not being given data. So requests were not served because of this quota management, and then to dynamically adjust it is also a tricky beast. So this was the main reason of the main challenges of hierarchical caching that they were using. Then they go on to talk about that on the contrary, they also used decentralized systems like BitTorrent, and they had in house static tree. They say that it's better for scalability, but then the point is that with BitTorrents, the decision is left to the peers, and peer is not aware of the global state. Instead, it is aware of this thing. local information, and because of that it is not able to take globally aware correct decisions. So the thing is that uh, this led to poor resource efficiency and also led to not optimal performance. Then let's talk about the design in some aspects. So this system has a couple of elements. One is peer. It is simple, provides a mechanism for caching and transferring data chunks, has a centralized control plane, does all decision making about distribution. Control plane is implemented by a small set of trackers. Then detailed state is maintained by each tracker, which helps them to make highly optimized decisions because it's the trackers know the complete global state. Workloads scale beyond cap of single tracker. So what if the workloads requirement is that a single tracker is not able to handle? Then they make use of sharding. So then with sharding comes different types of challenges. So we'll see those things in later slides. But then the tracker, what information does it have? It is a fine grain view of state that it manages. It also has coarse granularity of the entire state, which is needed for delegation. That will also come in the later slides. So tracker implements, the other important thing is about flexibility in terms of policy. So they say that we have modular interfaces for supporting different policies for caching and fetching data. And they have around 10 million peers that are managed by 112 trackers, which in terms of centralization is looks to be a decent value. So yeah, peers, trackers, and there are also some objects or processes known as super peers. These are large, long-lived caches. Peers and trackers we've already talked about. Okay, so what they say is that they build a ephemeral distribution tree. So suppose data source is the storage that has the data. Now, you know, we want to fetch data. Uh, so what happens is that tracker fetches data from the data source and it caches to the super peer, and then peer also fetches data from the super peer and caches it in its place. So what happens is these red pointers are the directed edges of the tree. So data from data source, data goes to super peer, and from super peer it goes to other peers, and peers can also fetch data from other peers which are there in their locality. So it's not like this peer has to fetch data from data source or from super peer. If the nearby peer has data, it will fetch it from there. And yeah, this tracker keeps all this information. So how does scaling trackers work? So there are a couple of things. Chunk size can be large. Geo sorted indexes for quick lookup is there. Their measurement shows that a single tracker is able to pull in around 1.5 to 2.4 terabytes per second. So further scaling is done, as I've said, by sharding across multiple trackers. So what is the issue with sharding? See, this is a case of sharding, like data is being fetched by peer A1 and also by peer B1, and you have two trackers. So now the problem, so sharding with this, we can uh, distribute the content to the peers, but the problem that is happening is, yeah, for this peer to get the data, it has to go to data source. So there is a cache miss involved over here. Also there is a cache miss, and then here also if it would have gotten data from peer A1, that would be better. So like issues, what is the issue? Leads to cache miss rate, which is kind of in this example twice. What is the solution? 2 levels of metadata resolution. What is that? Keep some information at every tracker. So tracker would, for peers that are owned by the tracker or managed by the tracker, keep chunk to peer mapping. And for remote peers which are not owned by this tracker, like here peer B1 is not owned by tracker A, so keep a mapping of chunk to tracker mapping. Like, okay, this chunk will belong, goes to which tracker. So this is the part of the delegation that they are talking about. So tracker sharding with delegation improves cache miss rate by 3x, and they say that in practice they are able to see 90% delegation success. And how is it happening is, I have the chunk, it says Okay, so this peer A1 is there. Now the data or the chunk is fetched by peer B1 from A1 and not, it doesn't go to data source. So similarly, so it's just a matter of making trackers intelligent enough even to know the location of the remote chunks, which are which where the remote peer should get the data from, and not just only they should get it from data source, something of that sort. So yeah, so references are OWL OSDI paper, the short talk video, these slides diagrams I've taken from their slide deck. Yeah, that's all from my side. So questions?